So moving from BI to the cloud, let's welcome Serban Mateescu. Serban is a software developer at Big Step. He has many years of experience in provisioning Kubernetes, distributed big data processing, distributed monitoring, and anomaly detection. Today he will share with us how to meet the unique challenges posed by monitoring millions of devices across hundreds of thousands of tiny geographically distributed data centers. So Serban, thank you very much for joining us. Let's see how distributed monitoring for the edge cloud works.
Cool. Thank you, Matej, for the introduction. My presentation today is called Distributed Monitoring for the Edge Cloud, and I want to have a little introduction now. My name is Serban Mateescu. I have a bachelor's degree in informatics from the University of Bucharest, and I've been a software developer at Big Step for the past 4 years. As Matej mentioned, I had quite a diverse range of projects while working at Big Step, such as Kubernetes provisioning-based software as a service platforms. So that was Lentic, and various distributed big data processing and anomaly detection. And right now, I'm working on a project that is related to this presentation that focuses around distributed monitoring. Before I get into the presentation, I want to make a quick note. 2 years ago, I also held a presentation at Big Data Week, and it was again about monitoring, about anomaly detection. That was a bit more practical than what today's presentation is going to be, because I have two aims for this presentation. First of all, I want to show you a cool way, a cool solution that that Microsoft came up with for solving a difficult problem. And secondly, I want to present to you an abstract way of thinking that can be applied to many other issues regarding the edge cloud. So without further ado, I'm going to get into it. First, just a bit of prerequisites about the edge computing. Edge computing is quite a new concept. I want to, in order to understand it, you have to know what the edge is. And if you search on the internet for definitions for the edge, you might find quite a wide variety of definitions. And this is because edge computing itself is an abstract term, and the edge from edge computing is even more abstract. And that is because, sorry, just I had a few issues. I think that you can now see my screen, right? Sorry. Okay, so regarding the edge computing, the edge, if you search for it on the internet, you might find quite a number of definitions, and this is because the edge it depends on the context. Like,
sorry, we're still not seeing your shared screen.
Oh, sorry, I'm having some technical issues right now. Is it okay now?
Now it's fine. Yeah.
Cool. Sorry, there was a I didn't press OK on something. Sorry. Good. So regarding edge computing, the edge has quite a number of definitions, and this is because the edge depends on context. So if you're talking about your personal environment and home, the edge might be the router. That's the edge device between you and the internet provider. But in more industrial cases, this might mean a number of services that the internet traffic passes through before going into the internet. So for the purpose of this presentation, just think about, you have to think about edge nodes as being devices, dedicated devices, or all sorts of things that are close to you in the topology. This paradigm of edge computing is something that is becoming more and more important these days. And think about it, as I told you earlier, there's a big number of devices, and topology is more important than ever because of this, because there's a whole web of things that that have to be taken into consideration. Like people say, like it's the Internet of Things, but on steroids. Like even your light bulbs might get IPs in the future. And a few things need to be adapted because of this. Like storage needs to be decentralized because the level of data exponentially increases, and computations computations need to be moved as close to where they are needed as possible, because you don't want to put strain on only one central unit. And of course, some major things have to be changed in order to keep up. For example, monitoring. And the old approach to monitoring has quite a number of issues when applied in the edge computing scenario. First of all, because there are many devices, there's lots of data, so a lot of data gets transferred from the sources to the central unit, and the topology is very complex, so there are many hops in the network, so the network is very stressed. And lastly, the computations and the storage are the responsibility of only one central unit. So computations get very slow, mostly because the level of data is really big. So what I'm proposing today is a distributed approach to monitoring. That means a tree of dedicated monitoring nodes, which I'll get into more specifically a bit later. So basically, each node should be responsible for a manageable number of edge devices, in this case, or other monitoring nodes. Storage should be distributed among them. There would still be many hops, but fewer data would be transferred. Because computations would be executed in a MapReduce fashion. So every query would be based on partial results from other nodes. But I will get into this a bit later. First of all, I want to talk to you about the main components of this model that I'm proposing. The monitoring agent, which I will use this symbol from now on to note it in future diagrams, has two functions. First of all, it's responsible for gathering and collecting the data, of course, and for storage. Basically, one monitoring agent has one shard of the whole database that is spread among the devices in the system that is monitored. And secondly, the computation node, notated with this. This is the predominant node in the query engine tree. It's basically a standalone software or a piece of code in a bigger service. It is able to respond to queries and provide partial results above in the tree. It has a number of data sources, these being other computation nodes or other monitoring agents underneath, and it is aware of the topology underneath it. I will get into this a bit later because right now I want to talk about the monitoring agent, which is the basic building block of this whole model. First of all, about data gathering. These are just examples because it really depends on what you are monitoring. In a data center, for example, you might want to monitor S-flow packets that are generated by routers and switches when internet traffic passes through them, and then these packets are then pushed into the monitoring agent. There might be SNMP traps or telegraphs that are pushed from servers to the monitoring agent that report certain, I don't know, alerts or stuff like that. Or there might be an internal service in the monitoring agent that periodically polls certain SNMP agents in certain servers. So with this, you might get data like CPU usage or disk usage or network interface traffic or stuff like that, or maybe things that are related to the chassis like temperatures or fan speed. And regarding the storage, there are, of course, we are talking about time series, so we need a specialized solution, and there are quite a few number of third-party solutions that are available on the market. There is Graphite, there is Prometheus or InfluxDB. Basically, they all do the same thing. They are databases that specialize in storing and retrieving things that look like this. This is an example of a query that will result in one time series. This is important for the rest of the presentation. This thing right here. This is a query function. This is the query string, which is in the Graphite format, and this query results in an array of data points. This array is called the time series, and these data points have two things: have a value and a timestamp. So, for example, here, what this means is that For the subnet with ID 123, the download in data center 1, the download traffic reported at 12 o'clock on the 6th of October 2020 was 2 gigabytes. Then a half hour later would be 0.7 gigabytes. This is just an example, and this query string is not something standard. It's an example for today's presentation. And other types of query, these queries should permit wildcards, and this is important for aggregate functions in the future. Like there's a wildcard for the ID field, so that the result would not be only one time series, but all the time series that match this query string here. So now that we have these prerequisites and we have the data stored in manageable quantities close to the sources of metrics, basically sharded, we can start processing it. So we introduce the idea of the aggregate functions. What aggregate functions are, for example, sums that are functions that take in a number of metrics, matching the query string, and apply an operation resulting in a single metric. So they take many metrics and result into one metric. These are two examples. For example, aggregate the sum of all the subnets download in data center 1. This would result in the sum of all the metrics that match the query string, as stated here. And this is an example of average. These are the most basic ones, but you get mean, max, moving windows, and all kinds of statistics related aggregate functions. But for the purpose of this presentation, later on I will show you an example of sum. Good. So regarding the moving forward with building the query engine tree, as I mentioned earlier, the query engine tree is built out of computation nodes and monitoring agents. The computation nodes do computation, of course, and the monitoring agents gather and store the data, and they also do a bit of computation, but it's not important. And really important to the basic building blocks of this tree is that the monitoring agents are the terminal nodes, and this is because they are the closest nodes to the sources of data. They are right beside the servers that are monitored. They are right beside the sensors that are sending data and stuff like that. So they are the the closest edge devices to the monitoring sources. Another thing that is important about this tree is regarding topology. As I mentioned earlier, each node is aware of the topology underneath it. Meaning that this node here knows that it's connected to this one and to this one and to this one, and knows that each of the nodes underneath have certain certain priorities. For example, let's say that this agent is in data center 1 and this one is in data center 2. This node knows that this topology is aware of these topology things, but above the node is not important because as I mentioned earlier, one computation node should be able to respond to a query. And this query is provided by computing the data from below it. Good. And another cool thing is that nodes can be redundant. As you can see, these two nodes are on the same level and they are connected to the same nodes underneath. So now we can consider them as being equivalent. So if, say, this node when being queried can have the choice of going this way down or this way down, because in its topology hash map, it would know that these two nodes have the same information. And given that everything knows all right, and that this is a deterministic system, if this node would choose this one or this one in a round robin way, the result would be effectively the same. Good. So now to a practical example of how this would work. The most basic one is just getting data. Okay. So we talked about the graphite format. This is a query string that would match all the RAM usage metrics for the servers in data center 2, and we expect the result to be something like this: a collection of time series, each having an identifier to it. This one is the metric for the server 1, this one is the metric for server. This node A is on top of these 3 other nodes, and it has a topology map So it knows that node B underneath is responsible for data center 1, and nodes C and D are responsible for data center 2, and that they are redundant. So when the query goes into node A, it processes the query string and sees that it needs data from data center 2. So then it looks into its topology map and chooses in a round robin way one of the two nodes. So for the purpose of this example, it randomly chooses node D, and then node D passes on this exact query to the monitoring agents underneath. These agents have data that was pulled from these sources, and they match the metrics they have with these with the query string. And let's say that this agent 1 matched with 10 metrics, agent 2 got 20, and agent 3 got 40. These are just random numbers. They then pass the query result to node D. The node E encapsulates them in one whole answer, and then passes it on forward to node A, and then this is the result of the query. At this point, it really doesn't, it's pretty much the same thing as, almost the same thing as the centralized model, because pretty much the same amount of data is passed through the network. But the cool thing about this this environment is when you take into consideration aggregate functions. So the second example is on an aggregate function. Let's say that we want to sum all the download metrics for all the subnets in data center 2. Okay, the result would be only one time series that would be the sum of these metrics that matched. Okay, so only one time series. And at first, the query would spread the same way as the standard one would. It goes to node A, then to node A knows that it has to look for information in node 2, and it looks into its topology map and sees that it can choose either C or D. It chooses D randomly, then node D passes the query down to all its agents. But and right now things begin to change, because agent 1 matched with 10 metrics, agent 2 with 20, and agent 3 with 40. But these agents don't forward 10, 20, or 40 metrics to node D. They first apply the sum function. And this, as mentioned earlier, results in only one metric. And agent 2 does the same thing and results in only one partial sum. And agent 3 does the same, and so on. And then they all pass each only one metric to node D, so that node D only has to do the sum of 3 metrics. And then it passes the partial result to node A, and then node A does sum of one metric, which is redundant. And then that's the result. So this is as map reduced as you can get. It's really simple to think about it, but when you get implementing is a whole other story. But this is how it would work, and let's study how things are right now for a bit. Like regarding the storage, storage is distributed only in the monitoring agents, so that there is no central unit that has to manage all these metrics. Regarding the traffic, well, there's pretty much little traffic that has to go through this environment. Like there's only one metric here, one and one here, and that's pretty much it. And regarding computation, this is the really cool part. Computation was moved as low as possible in the tree. Okay, so this node A and node D don't have much strain put onto them. The most strain is put onto these monitoring agents. But as stated before, monitoring agents should have a manageable amount of servers and sensors that are responsible for. So if this is respected, then everything should work as smooth as possible. Cool. So this is the theoretical part. I want to talk a bit about the practical part, about what Metrosoft did. When we decided to move into edge cloud scenarios, we knew that the monitoring was going to be quite a big issue, and that we had to change it. So then we came up with this solution, this big plan, and then after we got to the plan, we started working on it. And the first thing we had to implement was the monitoring agent, of course. And we started looking at the third-party solutions. We looked at Graphite or Influx or Prometheus. And if you worked with time series database in the past, you know that Graphite is the most lightweight of them all. But it was still not lightweight enough for us because we wanted our monitoring agent to be lightweight and run on devices with a really limited number of resources. So we built our own. um, it's based on a cluster architecture. Like it has a master thread and it has worker threads, and so there's almost no downtime. If one of the worker threads fails, then the master spawns another one. And the workloads between the workers is very well delimited. They are stateful, so that there is almost not almost there is no collisions or race conditions or any concurrency issues whatsoever. Regarding the internal architecture, there are a number of components. There is the SNMP instance poller. This service gathers metrics from operating system and BMC SNMP agents so that you get both CPU load, disk usage, RAM usage, or network interface metrics from the operating system, but you also get chassis related stuff like temperature or the speed of the fans from the server, the bare metal server itself. You also have the S-Flow listener, which listens for S-Flow packets reported by routers and switches so that we can monitor the traffic that goes in and out of data centers. And of course, there is the database, which is very Graphite-like, but it has many optimization for our needs. So first of all, it uses the same query protocol, like all the examples you've seen before with the wildcards and stuff. It's the same thing in our implementation, but regarding the storage part, it's a hybrid solution. Some data, all the metadata is cached in the in memory, and also some other data, some data points are cached in memory, so that certain operations can be executed really fast, and the I/O on the disk is minimal, and it also has downsampling and all these other cool features that most time series databases have. Lastly, there's the alert service, which can be configured by the user, and when certain custom thresholds are exceeded, it sends notifications to the node above and the node above and so on, until a central unit that is responsible for sending emails or SMS notifications to the user about these thresholds. And this is the monitoring agent. Regarding the query engine itself, we got the basic concepts down, but it's still a work in progress. What I talked to you, this project can be summarized in a few sentences, but when you get to implementing, there are a lot of corner cases that have to be taken into consideration in order to make sure that computations are executed as low as possible in the tree, because you have to optimize a lot of logic in order to get to a system that is very performant and doesn't put strain on any part of the network or on any dedicated device whatsoever. So we got the basic concepts down, but there of course are still a lot of some things that we have to implement in order for everything that I mentioned earlier to be taken into consideration. But for example, in the next month or the month past that, this system is going to replace the old approach to traffic monitoring for billing purposes in BigStep. Until now, of course, it was the old centralized system, and it's proved to be very inefficient because the computations needed to be done on the master machine were really huge, and they started cluttering up really easily, and it was really a pain to work with it. So now we are not slowly, we're really fastly moving to replacing this old system with what I told you about today. So yeah, that was pretty much everything that I wanted to present to you today. The most important thing that I want you to learn from this is that this monitoring issue the model of this problem, if you take it in a meta way, in an abstract way, can be the basis to solve all sorts of problems that might arise in the edge case, in the edge computing scenario. So this is just an example of how you can think about solving problems in this environment. So yeah, thank you. This was my presentation, and I think we can move on to the Q&A.
Thank you, Sherban. The first question is, what were the main challenges when you guys were implementing the monitoring agent?
Well, it was not necessary. The main issue was a meta one, meaning that as you can see there, as I presented it to you, the final architecture is very modular. So we wanted to make sure that everything is as neatly organized as possible, because the corner cases are trust me, you can't think of the things that we had to solve in the past few months. It's really, really challenging. So organizing was, I think, the biggest issue of them all.
So that's the second and the last one. If you'd had to name one thing that was most complicated to track down and to monitor, what would it be?
I think that this is not necessarily related to the presentation itself. This is actually an issue regarding old servers that don't have that their documentations are not available anymore. So we had to manually dig through OIDs. OIDs are IDs used by the SNMP server agent to identify resources, and we had to manually dig through all the results so that we can find the temperatures and fans and all these kinds of stuff. And then each server had its own OIDs, and it was a mess. This was the messiest part of them all, which sounds easy, but it was the most nerve-wracking one.
Sounds easy, but it's probably not, as it always happens.
Yeah.
Sherban, thank you very much.
Thank you,
Guys, we have reached our second networking break. So feel free to grab another coffee, a glass of water, and check out the Digital Expo. There, as I have told you, we have a lot of surprises waiting for you. So we'll be back here in 15 minutes after the break. Just remember that each session is broadcasting independently. So make sure you check the live sessions tab when returning. And we'll see you soon.